Okay, well,
So as is my lovely tradition here, let me say a couple of words about the next homework. Okay, so here's the homework for next Friday. The first one, what R be a commuter bring with identity and S be a multiplicative subset of R. And I'm going to explain what that means, but what it means, what you think it means, perhaps, that if you have two elements in S, then the product is still in S. That's multiplicative means product being two things in the set, still in the set. If I is an ideal such that I intersect S is empty, so there's no overlap, show there is a prime ideal that is maximal with respect to the property that the prime ideal intersects. So in other words, you can take this ideal I and grow it. So if you have I and S multiplicative, you have X and Y in here, then XY is here also. If they miss each other, then you can sprinkle a little fertilizer on it and grow it to a prime ideal. Well, if there is, right, show that there is a prime ideal that is maximal with respect to the property intersection is, there we go. Number 3, use the previous result here. Actually, number 1 is very important. It comes up in community algebra all the time. This is actually a Zorn's lemma argument, by the way. Number 2, show that given any proper ideal, then there is a I and R. Given any proper ideal I and R, then there's a maximal ideal that's contains that. We've already proved this using Zorn's lemma. This is a big thing we did last time. Using 1, there's a quick way to do it. But of course, 1 requires Zorn's lemma as well. So number 3, we talked about the radical of an ideal. Given an ideal I, the radical is everything in R such that a big enough power of X bounces down back into I. This is kind of an interesting characterization. The radical of any ideal, if you want to compute it, another way to compute it is you intersect every prime ideal that contains I. All right, so the radical is the intersection of things. One of the containments is really easy. The other one is a little bit tougher. Number 5, application. What does this? Tell me what this says in the special case that I is 0 I. And finally, number 4 is just let's get our hands dirty and do some computations. You'll be able to do this after today for sure, because the Chinese Remainder Theorem is quite helpful. Suppose you have Z 18,000, right? And I just mean this range. Count the units. How many units are in here? And in number 3, what is the proportion of the 0 divisors that are nilpotent? So what's the proportion of nilpotents among the 0 divisors? Okay, any questions on that? All righty, so let us continue. I'm gonna do the last time we did this theorem here, where we talked about when we can decompose R into a direct product of its ideals. That's what we proved last time. I'm going to prove something here that's a little bit more general that the Chinese Remainder Theorem follows from. I'm not going to prove it. I'm going to state it. And I'm going to state it in generality. I will leave this for an exercise. As a corollary, I will get the Chinese Remainder Theorem, but I will actually prove that at least in some small way. So here's a more general theorem. Let A2, A1, the ideals such that and let me point out, so this is a kind of this weird condition. R squared plus AI generates the whole ring for all one. In particular, this condition always holds if R has an identity. Because R, or in fact, if R squared equals R, right? More generally. So if R squared equals R, so in particular, if R has an identity, and this always is the case. And AI plus AJ equals R for all I and J distinct. If B1, B2, Bn, and R, then there exists this is sort of B is sort of a master solution to set of equations. Such that B is equivalent to BI mod AI. And just to make sure that B is uniquely determined up to congruence modulo the ideal A1 intersect A2 intersect. And just to clarify, hopefully, so that we all know what I mean by this, what this means is that B minus BI is an element of the ideal AI for all. That's what this means. Okay. Let me give you a corollary to this. Like I said, I'm going to leave this for an exercise myself. Muck around with this, or at least muck around it in case I have an identity. I'll give you a corollary that follows from this, but I will prove it at least in the case of. Suppose A1 to AN are ideals. So you have this collection of ideals in R. Then there is a monomorphism of rings. There exists monomorphism of P from R mod A1 intersect A2 intersect N. R mod A1. And if R squared plus AI equals R for all I, and AI plus AJ equals R for all I equal not J, then this homomorphism is in fact an isomorphism. let me, so let's go through the proof of this corollary, and I'll show how it connects to the previous theorem, and then I'll give you something really more concrete that you can kind of take home with you. Now, the claim is we have this collection of n ideals bar, and there's a monomorphism from here to here. Let's just do this. Consider F consider this function here. Consider the easy function, if you will, that takes every element of the ring to its coset, R bar mod E A I, right? This is it's easy to check that F is a ring homomorphism. It's certainly a group homomorphism. We've seen this kind of thing before. And it's easy to check if multiplication works as well. I expect this thing to neither be one-to-one nor onto, right? I don't expect this to be onto, and I certainly don't expect it to be one-to-one. For example, if R is in A1, right? That's one thing. Well, I'm sorry. If R is in the intersection of A1 up to AN. If R is in every one of these ideals, then the image is 0, right? And so really what I need for this to be one-to-one is for R to be contained in every ideal. So in fact, let's imagine kernel F for all I say I. So and so what we can conclude from this is kernel F and so this gives me the statement that I need. So F induces monomorphism. P from R on A1 intersect A2 intersect AN R on A1 or homomorphism theorem. Because this thing contains the kernel. Now, next step. There's our monomorphism brain. Didn't really need much of anything, but what do we need for this to be an isomorphism? Well, we need it to be on. Right? And that's exactly what this theorem gives us. We need to find an R that covers everything here. So in other words, if I have the coset B1 plus A1, B2 plus A2 up to Bn plus An, if I can find this magic B, then that magic B will cover that arbitrary collection coset. So that's why this is a corollary to this voluntary equivalent by given means. Let me actually prove the corollary as an entity unto itself. Let me show that under these conditions that we do get well, at least I'll get you started off to show that we do get a isomorphism. let's suppose that one is an R and two. I'll just make my life a little bit easier here. Now B from so to show P is onto prices to show image of F is R A1 R2, or we call F of R, is because of R R. Right, because remember, from the original homomorphism we constructed, we have F from R into this, and so this induces a homomorphism from F mod this A1 up to AN into this thing right here. And so if we have that, that the original F is onto, then we get our isomorphism that we wanted. Okay, any questions? So how do we show this is on? Well, we know that A1 A2 is R. So there exists A1 A2 such that A1 plus A2. So there, I've used my little shortcut that R has the identity. Again, you generalize to prove this gives you the idea. Now, what I need to do is I need to show that given because that there exists R such that R equals I'll see if I remember how to do this. Let alpha be x minus y, where we mean that way. Notice that alpha becomes A1 plus A2 alpha, because A1 plus A2 is 1. Everybody okay with that? So alpha A1, alpha A2 is alpha x minus y. And so rearrange this equation a little bit. So I'm going to take this one here. I get y plus alpha A2 equals x minus alpha A1. Massage that a little bit. And let this be R. So notice that F bar is R plus A1, R, let's say 2. I can write R, I can write R either of these ways, whichever way suits me. And this is X minus alpha A1, A1, Y plus alpha A2, plus A2. But of course, alpha A1 is here, alpha A2 is here. So X plus A1, alpha A2. And there's that is good, these two. And in general, for N, you proceed by induction, but it's pretty much the same thing. Okay. Any questions on that? Yes.
Why the line above the last line is that equal to R?
Oh, I just set that equal to R. This is what the R is that I'm gonna plug into my app. Yes.
Where did we use the R squared plus I equals R?
We didn't. We used this, which is a stronger condition, right? But you can massage this proof and do it in a more general situation. But I'm a lazy man. And where this came up was right here. Because I know that A1 plus A2, where are you now? Did I not write that down here? Oh, yes, A1 plus A2 equals R, and since R has an infinity, I can do that. So that just made my proof a little easier. For example, so why is the Chinese remainder theorem useful? Well, so for example, modest. Let's do. Notice that 1200. Let's see if we can do this right. Let's see if that's, so this should be T4. There's 100. By the Chinese remainder theorem, notice that the ideal 2 to the 4th intersect 3 0 or equals notice that these are all proper ideals. So the Chinese remainder theorem actually gives us that C mod 1200. And so actually, for example, if you're in things like coding theory, or if you're doing stuff with finite fields, it's important, for finite rings, it's easy to pick stuff out here. This is actually isomorphic.
About the notation of things in parentheses.
I mean, the ideal.
So,
I mean, the ideal generated by 16 plus the ideal generated by 3 plus the ideal generated by 25 is all of the in Z, right? Yeah. So these are all Z, and what this is, because remember what this is another notation for Z mod 1200, and the intersection. Chinese remainder theorem gives us this right here. And so if I asked you to do something like count the units, Well, think about it this way, counting units in Z mod 1200 is a rather daunting task because you have to go through and try to pick out, some first 1200 integers, which ones are relatively from 1200. It's obnoxious. But well, this is a much easier problem, right? Because 16 is power 2, and the units are everything mod 16 that are relatively prime to 2. So it's just the odd integers. So there's 8 of them. The code says 1, 3, 5, 7, all the way to 15. How many units in C3? There's 2 of them. Because 3 is a prime. And so everything is relatively prime 3, just 1 and 2. How many units in Z25? You want to tell me that? Yeah, that's right. Here are the ones that aren't relatively prime 25. 0, 5, 10, 15, 20. 25 take away 5 is 20. So just like that, the number of units, to be a unit, you've got to be a unit in every coordinate, be invertible, because the one here is 1, 1, 1. So you got to be invertible. So it's 8 times 2 is 20. It's this 300. 320 small 1200. Everything else, since it's a finite ring, has to be 0 divisors. Okay. Yes.
So you put down the ones that were relatively prime.
That's right. The ones that had a factor in common and took them out. Because what you want is you want the stuff that has no factor in common with 25 or equivalently no factor in common with 5. Okay. Any questions on that? Yes.
So to be a unit in Z16, it needs to be coprime to 16. But then,
Which is equivalent to coprime to 2.
right. So then that wouldn't necessarily also be coprime to 3.
No, it wouldn't. Right.
So, but you just multiply them all together.
That's right, because you're considering these as separate entries, right? Because unit here, unit here, unit here, you don't cross multiply. So for example, if you have 3 bar, 2 bar, and what's something like here, 6 bar. I mean, how obnoxious is this? They've all got factors in common with each other, right? But remember what the multiplication does is it is coordinate. There's no crossing over, right? So the inverse of 3 should be like 21. 3 16, so that's yeah, 3 times minus 1. So it should be minus 3. So it should be there we go. And this should be 2. And the inverse of 6 mod 25, 26, 1, 36. Yeah, whatever the inverse of 6 is, it should be 1 mod 5. 26. Yeah, it should be 17. Yeah. So if you multiply these out, you get the first coordinate 33, which mod 16 is 1. And you get 4, mod 3 is 1. And you get 102, which mod 25 is not 1. Yeah. one on line. None of these will ever work, so it's gonna be 26, 50, 76, 126. There. That's 126. And see that, and that actually shows the convenience because, you know, looking at, well, and here you can pick out I mean, despite my struggles for the last quarter, and I picked this up fairly easily. Now, if you figure out what this element is, by the way, you know how to figure out what the corresponding element is in Z mod 600? Or, I'm sorry, Z mod 400. So this is the other part of the Chinese remainder theorem. Let's figure out what this is. So whatever this should be, it should be equivalent to 6. So whatever x is, should be equivalent to 6 mod 25. Should be equivalent to 2 mod 3, and it should be equivalent to 3 mod 16. So, let's do these two first because they're the easiest, or they're the biggest. So let's find the solution mod 400. So if it's equivalent to 6 mod 25, then basically 6 is not equivalent to 3 mod 16. So basically that's 25. This is 31. Let me point out that to be equivalent to 3 mod 16, it's got to be odd. So now I can jump by 50. So this doesn't work because when you subtract 3 is 28, and if it's 50, when I subtract 3 is 78, that doesn't work. When I subtract 3 it's 128, that isn't visible, right? So whatever we have is x is equal to 131 mod 400. These two, right? Notice that 131, you subtract 6, you get 125, by this, you subtract 3, you get 128, 16. Now, does this work mod 3? Right? When you subtract 2 from this, you get 129. That does work. So it's actually the corresponding element is 131 here. All right, because 131 satisfies all three of them. Everybody agree with that? Everybody see how we get that? Let's figure out what the inverse is. The inverse, which I'll call y, should be equivalent to 11 mod 16. It should be equivalent to 2 mod 3, and it should be equivalent to 21 mod 25. Everybody okay with that? So again, let's do this and try to get the equivalence down to mod 400. It has to be 21. Let's see, 21 itself doesn't work. When you subtract 11 from it, that's not 16. But again, to subtract 11 and be even, I can go ahead and jump by 50. So 71 minus 11 is 60. That doesn't work. 121 minus 11 is 110. That doesn't work. 171. When I subtract 11, 171, I get 160. So the inverse should be 171 mod 400. So I've got these two conditions satisfied because 150 is divisible by 25 and 160 is divisible by 16. Now, is this equivalent to 2 mod 3? When I subtract 2, I get 169. That works. And so, what can I do? Well, jump 400 because let's try 571. Does that work? When I subtract 2, I get 569. Nope. It's gotta be the next one. Another 400. I get 971. Notice that 971 satisfies all three of these equations. And these two should be inverses of each other, not 1200. And I'm so embarrassed, I should turn off the recording now, since I'm getting out a calculator in a freaking graduate class. Sorry. But let's see what we get, shall we? I probably should attempt to test myself, but I'm going to do it anyway. So if I take 131 times 971, I get 127,201. So when I subtract 1, no, here. So they were indeed inverses. So, right, which would you rather do? This or this, right? The only reason I was able to do this quickly is because I knew what the answer was. So that's kind of the power of the Chinese Remainder, or one of the powers, I should say. Any questions on it? Okay. Speaking of factorization, we will now delve a little bit into one of my personal favorite topics. So, my default from here, and for most of the course, actually, the rest of the time, my default will be all rings or community. One, if there's an important time when we can deviate or I need to point something out, I will certainly make mention of that. Factorization without one is very surprisingly a mess, as we probably saw with ideals here. But if you think about it, you start with a ring and just think about the addition, and that's all you think about. This is an abelian group, which is a subject from the past, right? If you want to study what makes rings different, then factorization R plus or R times, right? You want to study that, and sometimes you want to study how the factorization intermingles with the addition. Let me give you a little. So, if you ever want to have a hard problem, let me point out something about, let's say, community rings. Let me point out something about the integers. The integers are everybody's prototype ring, right? That's the first. That's the genesis, so to speak, of thinking about rings as you think about the integers. As an abelian group, the integers, soup's easy. It's cyclic, right? Plain and simple. Every cyclic infinite group is isomorphic to the integers. Very well understood. It's got one that generates it. 1 and 1 is 2, 1 and 1 is 3, and so forth. Easy peasy, lemon squeezy. Multiplicatively, the integers are easy because you have the fundamental theorem of arithmetic. Up to a sign, everything bigger than 1, or every integer other than plus or minus 1, is factored uniquely into primes. How many of you all knew that? Fundamental theorem of arithmetic, right? So, in other words, if you look at the quotient field of the integers, if you take the rationals and throw out zero, and let's just take the positive rational, so you don't have to worry about sign, but that's not a big deal. Every positive rational can be expressed uniquely as a product of primes too. Only now some of the primes may have negative exponents, right? So easy. It's a free of zero easily, right? The integers, multiplicatively easy, additively easy. If you want a hard problem, ask yourself the question that mixes those problems. Fermat's last theorem, right? What does that say? If you have x to the n plus y to the n, it's not equal to z to the n when n is bigger than or greater than 3. What are you asking? When can the sum of two nth powers be an nth power? Nth powers, multiplicative. Sums, different. The prime twins problem. Are there infinitely many primes that are 2 apart, right? Prime is multiplicative problem. And 2 apart, that's an additive problem. The Goldbach conjecture. Any even integer greater than or equal to 6 can be written as the sum of 2 primes or 2 odd primes. Again, the prime, multiplicative, and summing them is something different. You can make, when you mix the two easy properties, it gets difficult. But we are going to talk about factorization. So, what if you tell sort of lay the ground? A non-zero. Well, actually, I'm going to take non-zero. An element A in L said divide B and R and sometimes write A divides there exists X in R such that B equals X. Let me point out, and this I think is, you can sort of see how this works, right? B over A is X, right? If you think about it kind of intuitively. This is what we need to divide. We say that A divides B. If B can be written as A times X. Notice, technically by my definition, this means that 0 can divide something. What can 0 divide? What can the element 0? If it divides something, what does it have to divide? Notice, technically, that 0 can divide 0. Because if you take A equals 0, then this is 0, right? The reason that people usually avoid this is because usually, if you say something like 2 divides 4, well, let me say, if you say something like 2 divides 6, that is because 6 equals 2 times 3, right? And that 3 is uniquely determined, right? 10 equals 2 times 5, and that 5 is uniquely determined. If 0 divides 0, any X works, right? So the quotient, if you will, is not well defined. But we can say, if we like, that 0 divides 0.
But outside of the field, isn't that also the case? Not just for 0, but that the X is not uniquely defined.
If you have, if you don't have 0 divisors, then it's uniquely defined. All right. So if you have an integral line, which is usually around 5, then it will be mixed. Okay. Now I will say, not 0, A divides B and B divides A, we say A and B are associates. So we say that two elements are associated if they're non-zero and they divide each other, right? So in particular, any element is associated to itself. Okay. Theorem. Let's let R be commutable identity, A, B, U, and R. Number one, A divides B if and only if the ideal B is contained in the ideal term phi. So I like this one because it gives me an ideal theoretic characterization of division. A divides B means that this ideal B is contained in the ideal term phi A. Number two, A and B are associates if and only if three U and R is a unit. Let me mind that notation. That notation is units R if and only if U divides R, all R and R, if and only if the ideal generated by U is all of R. Number four, the relation A squiggle B if and only if A and B are associates with equivalence relation. On R minus 0. And finally, here, A equals BU with U a unit in R, then A and B are associates. And if R is an integral domain, we converse poles. Any questions? Let me sketch out some of this to kind of finish up today. Oh, and also while I'm thinking about it, let me plug the math club. Chris McMahon, who's in our statistics group here, and is very involved in all kinds of stuff like this, was kind of a key player in sort of doing some of the COVID analysis around here. He's going to talk about that today. So I highly recommend it. He's a good speaker and it should be very, very interesting. Right. So if A divides B, that means B equals AX. Therefore, B is then the ideal generated by A because it's X times A. So And conversely, if it's contained in A, B, and that will by, so B. This is kind of the theme of the proof. Let me do the second statement of 5. If R is a domain, then an A and B are associates in commerce whole. So suppose R has no non-zero zero five. Hypothesis, I already know that R has an identity because we assume that about the ring. And suppose A and B are associates. So this means A divides B and B divides A, which I can translate to B equals AX and A equals BY. This first statement is A divides B, and the second one is B divides A. Replacing B by this, I get A equals AXY, which implies 1 equals XY. So Jared, I think this addresses the question we were asking earlier, right? If a domain is, you can cancel things to get 1 equals XY, and so X and Y are both units. Okay, any questions? Okay, how about out there? Any questions out there? If not, you all have a good weekend, and we will see you on, don't forget you got homework due today, and we'll see you on Monday.